So in the last two videos, we did two things. Number one, we did some intuitive sketch about the proof obligation as a sequence for invariant preservation. And number two, we spoke about the various formal components that you should really understand that's extracted from your model. They will be used to really formally state the proof obligation. And having done these two things, we are now ready to really see the ultimate proof obligation rule as a sequence for invariant preservation. Let's take a look, and then we'll also try to draw some connection to our model M0. All right, so we're gonna use all the formal components C, A of C, V, I of CV, and E of CV, right? And by now, you should really understand what each one of them really means. Okay, so this will be the formal rule of invariant preservation. And here you go. All right, so that's every component over here is something that we've just discussed in the last video, right? And over here, I also try to use the color over here to really say this part over here is really the assumption about the pre-states. And this is really something we would like to prove in the post-states. Okay, and it's also important to realize that when we say invariance with a particular index, we will be able to refer to either invariant number 1 or invariant number 2 for our model, right? That's also the notation we spoke about. Let me now switch to iPad, and then let's now talk about this rule very quickly, just give you a little bit more insights, and then we'll ask you a few questions, well, just one question, and then we'll see how we can generate the entire list of proof obligation that's relevant to invariant preservation. So that'll be the plan. All right. Let's now do the annotation. To start with, this of course is our model M0, our initial model. Everything we want to generate from here is going to be based on whatever we have declared in the model over here. And this will be the proof obligation rule for invariant preservation. So this is the rule here. So this will be the rule of proof obligation, specifically to invariant preservation. Okay, I'll just say IP, so you will know what I mean. Okay, and notice that this is only for a single event. For a single event, meaning that if you want to have multiple events to be covered in your model, you definitely should instantiate this rule for multiple times. We'll see. Okay, for a single event, let me highlight that. It's very important, otherwise you might just get confused about how the rule is supposed to be instantiated, right? It should be a single one. Over here. All right, let's now take a look at the components over here. If you recall the syntax and semantics for sequence, there's a turnstile, and we are using the vertical formats for the sequence. And let's now talk about it. So this part over here, let me use a highlighter here maybe. So this part over here is the hypothesis, right? That's or assumptions. So these are the hypotheses we can make. And this part here, after the turnstile, this will be the goal or the conclusion, right? This part over here will be the goal. This part over here will be the goal. And I want you to pay attention to what I'm trying to do over here. You can see here we said we got axioms, we got invariants, and also we got the guard for the events that we're currently considering, right? We can only consider one event at a time whenever we instantiate a rule. So let me just mention that here. So this will be the guard, and also for the effects, right? So we talk about the guard and effect for just only a single event. So this will be the guard and the effects of the single event under consideration. Under consideration. All right. It's really important to get every bit of detail actually accurate. So guard and effects of the events under consideration. The events under consideration. All right. And I want to also emphasize that over here, you can see we got V over here. So that'll be the evaluation for the invariance in the pre-states. And the G over here will be the guard for the events that will also be evaluated in the pre-states, right? So here we talk about the pre-states. Something we can assume before the transition occur. Pre-states. If you look at the informal meaning, when we did the informal intuitive sketch, you will see that's exactly what I said. But here, we're just making that precise mathematically. So this V over here will be the pre-states. And if you look at the effects over here, which we also spoke about in detail, I'm not going to repeat to waste your time. But if you take a look at over here, the effects, right? Let me remind you very quickly, this part over here is really about the post-state value in terms of, right, let me use the acronym, in terms of pre-state evaluation, pre-state expression specified in the events action. I should really say actions because in general, there might be multiple actions for a single event. All right. So let's now highlight the important phrases over here. So we talk about the post states value over here that will be expressed in terms of the pre-state expression. Okay. Let me use the lighter green, if I may. And also that will be specified in the events action, right? The events action, like a before-after predicate, right? Just remember, everything should really come together. So that's the before-after predicates of the events, right? All right. So what we're saying is, assuming that the axiom, invariant, and guard all evaluate to be true in the pre-states, we should be able to prove that the invariance is still holding in the post-states, and the post-state is expressed in terms of the before-after predicate. What is actually expressed in terms of the pre-state value as specified in the before-after predicate. That's what we're saying, right? And this part over here is also a very important detail over here. When we say I over here, right? So this is the index of an invariance condition. Well, we said before, for example, in our initial model, we got two indices, right? Index 1 and index 2, right? That's what we spoke about earlier. And let me annotate one more thing, just came to my mind. And then we're going to see how this rule can be applied, can be instantiated to our initial model, right? And we'll get there. But I want to mention just one more thing. So the guard over here is really about to really say the event is enabled. That events under consideration is enabled. Right? We're assuming that the event is enabled, and also the invariant is satisfied, and also the axiom is also satisfied. We're gonna execute the event somehow, and then the effects of the events is specified in its before-after predicate should really result in a post-states that is going to satisfy also the invariance. And this rule is only also for not just that, it's for a single event, it's also for a single invariant condition. So that's the new information I'm adding from before. Okay, so here I can definitely add it to. Okay, you can see here I say for a single event, right? Okay, for a single event, and also for a single invariant condition. So we talk about two things over here. For every invariant condition and also for every event, you should have an individual proof obligation rule to handle that. So we talk about some multiplication over here, right? I'll get to that more precisely in a moment. Okay, for a single invariant condition, right? And also a single invariant condition. For every single invariant condition and also for every single event, we should apply this rule once, right? For our initial model, how many such proof obligation rules should we produce as far as invariant preservation is concerned? That's a question, right? You will see a similar question on the slides over here. Let me present a question over here. So accordingly, how many sequence should be proved, should be generated and proved, right? So the answer to this is, there are two dimensions over here that we're going to consider. One is about how many events there are in the system, meaning that how many possible transitions you can make for each state. And number two is about how many invariant conditions that should be preserved, right? Let me talk about these two aspects over here. It's quite important. Okay, so number one, we want to talk about if number one is really about the number of events, like a state transitions we have. And the second aspect is really about the number of invariance condition. And we're going to talk about each one of them individually. And to really work out the answer, you should really multiply them together so you can consider, so you will be able to consider all the possibility, all the combinations, right? So that means we're going to actually do the following, right? Think about for our initial model. Let's see that particular example for our initial model. Okay, for our initial model, how many events do we have? Let's think about it's more like a set of indices, right? So think about we got ML out and also we got ML in. Right? It's a set of two events. We got ML out and also we got ML in. And what's its cardinality, right? I'm gonna just put a mathematical symbol. So mathematically, I can just use the vertical bar, right, over here to say its cardinality, multiplied by the cardinality of how many invariant conditions we actually got, right? How many? We got invariant number 1, invariant number 2 over here. So it should be also the set of invariants, invariant 0, 1, and also invariants 0 and 2. Right? So overall, we got this cardinality will be 1 and 2. This cardinality will be 1 and 2. So we got 4 in total. So the idea, the answer should be 4. In total, there should be 4 sequences that will be generated for this particular model as far as invariant preservation is concerned. I'm going to show to you 2 of them, and then for the other 2, it will be your exercises. All right? Let's take a look. And also, we got to name each proof obligation. We're going to name each proof obligation consistently and systematically. Okay. Let's see the naming first. The naming itself is actually quite straightforward. Let's enumerate that. You should really put first of all the event's name. So either ML in or ML out. Let's say start with ML out. Okay. So the naming. So we got ML out, and then you want to talk about which invariant condition, which could be either invariant 0, 1 or invariant 0, 2, right? ML out and invariant 0 and then 2. And what kind of proof obligation we are talking about? We're talking about the proof obligation related to invariant preservation. And remember earlier we said that this particular sequence over here, let me just show to you over here. Over here. You can see that's the rule, the name of the rule, right? So since we're talking about invariant specifically, invariant preservation, the name of the rule. So we're going to put inf over here. All right, so that's the naming convention here. You can see for invariant condition 1, invariant condition 2, for each one of them, we have to make sure ML out, the same events, will be able to preserve them after the transition, given that it's enabled. And we're talking about invariant preservation, right? So we got 3 components over here. And the first part, of course, is the event. And the second part over here is about the individual invariant condition, just a single one, invariant condition. And the third one over here is about the nature of the proof obligation. So you can think about the kind of proof obligation, right? You can see I'm only listing 2. I'm missing 2, right? So that would be your exercises you can see on the slides, right? But that should be rather straightforward to work out exactly what the other 2 should be that would be related to MLN, right? So that'll be your exercise. Now, what I want to do is I want to show to you how to instantiate the proof obligation for this one here, and also how to instantiate the same rule for this one here. We got 2, right? So think about this is number 1, and this is number 2, right? Let's see, use our example. So for number 1 over here, it's going to be a sequence, right? It's going to be a sequence over here. Going to be a sequence. And then we're going to include what? Okay, let's see here. axiom, first of all, what's the axiom? Axiom would be D is a member of natural number. So D is a member of natural number over here. And also the invariance evaluated in the pre-states over here, right? I think I should be more actually here. Be careful over here. I think that's right, but I didn't really mention. When we want to prove the goal, we want to be specific about which invariant condition we want to prove. However, when we make the assumption, we can assume that all the invariant conditions, including those that we are not really proving, we can assume that they actually hold in the pre-states, right? That's also something I forgot to mention, but it's good that I noticed that, right? So you want to really say that this part over here, I over here, is about all the invariants can be used as the assumption to prove only a single invariant condition. So these will be all the invariants, right? So let's now see. So what will be all the invariants? All the invariants will be here. Will be this one here, and also this one over here, right? So let's see. So it's gonna be n is a natural number, and also n is less than or equal to d, right? So let me just move this a little bit upwards over here. Actually, that's fine. Okay, let me put it here. Okay, so we got n is a natural number, and also n is less than or equal to d. So these are the three things I can put, right? Okay. So what we have done so far, we have listed the axiom here. We have listed all the invariants over here. And then we should also include the guard for the events. But as I said before, we have a very special case for our initial model. The guard is simply just true, right? Again, so the guard over here would just be true for the guard, meaning that both events will just be enabled always. And I also explained before, due to the identity of conjunction. So if you simply put something that's actually true over here, it will be as if it was not there because it has no effects. So I'm going to ignore that, right? But you should know, if you really got some guard for your events, which we might have when we revise the events later. So we may have to include something that's not true over here, but that's for later. Right, so that's about everything. So here it's just true, so we don't really list it for the special case. And we're gonna only include one specific invariant condition. And for number one over here, we are talking about invariant condition number one, right? So what we're gonna do is we're going to put invariant condition number one over here. So which will be n will be what will be the post value for n? According to the before after predicates, it's going to be n plus 1. So I'm going to replace it, right? Remember, we talk about the effects, right? So that's something you may want to review. We'll talk about invariant condition for I. This particular invariant condition index 1, it should be satisfied with the post-state value n prime replaced by the effects on the pre-states, in which case it would be n plus 1. So that's why I'm going to put n plus 1 over here, and then it's a member of the natural number, right? Let me just be more precise, be more explicit over here. In the invariant, it looks like an n is a member of natural number. In the post states, this is something we did earlier in the earlier video, but let me repeat it because it's so important. I don't want you to get confused. Okay, so over here, if you think about in the post states, right? What we want to say is, we want to say n prime is a member of the natural number. However, to really make sure we can actually prove things with the pre-state expressions only, we're going to replace this over here. n prime is going to be replaced by, in this case, n plus 1. So that'll be the effects. n plus 1 is a member of the natural number. So that's why you see n plus 1 over here, right? So this is the first proof obligation, right? You will definitely see the also the written version on the slides as well, but I want to mention this first. So that'll be number one. Okay, you can think about this one over here. This one over here is corresponding to this one over here. All right, for this particular invariant condition 1, which is over here. Right, let's now talk about number 2, right? But on the slides, you will see the name is actually placed right beside this particular rule. I don't have the space for that, but you will see you see the idea. Right, let's now do the second one very quickly. Okay, And for the second one over there, we're going to have just the same things over here, right? You can see this part will just be the same axiom. Well, sorry, I take it back. It will be, in general, the only thing that might be different will be the guard, because we're talking about, we may talk about different events. But in this case, yes, it's the same events, so it will be the same, okay? So for the second one here, we'll still talk about ML out. So the guard will still be true, meaning that we don't need to put it. So we only put the axiom and also all the invariants. So for this part over here, I can just copy from before. So I can say D is a member of N. So that is the constant, the axiom. N is a member of natural number, right? So this is the invariant number 1. And also N less than or equal to D is this, right? And then I want to have these as a hypothesis. So after the turnstile, I'm going to put the goal. The goal will be now the invariant number 2, right? That's what we need to include. Invariant number 2 is over here, right? So let me just help you once more, okay? For invariant number 2, let me use purple over here. For invariant number 2, let me put it here. For invariant number 2, is if I want to evaluate this in the post states, basically I'm saying n prime less than or equal to d. But to really put into the sequence over here as the goal, I need to put the effects of the events as, in terms of the pre-state evaluation or pre-state expressions. How do I do that? Well, since I'm still talking about the same events over here, that'll be n plus 1, right? So that means this part over here is going to be replaced by n plus 1 less than or equal to d by applying the effects, right? So that's why I'm going to put over here. Let me just wipe it out. Okay, so I don't. Okay, let me just delete this. Okay, so it's going to be, let me just put also pink, n plus 1 less than or equal to d. So this will be the second proof obligation associated with also the ML out. Right, so these are the two proof obligations. These are the two, right? It's really important for you to see exactly how to, number one, how to understand this proof obligation rule in general, and what each components are, which we, what each component is, which we spoke about earlier, and also how you can systematically name the proof obligation and to work out exactly how many proof obligation there will be, right? It's so important. Okay, let me just highlight one more thing. Okay, you can see here, n plus 1 is a member of n. So this is corresponding to invariant 0, 1, right? Which is over here. And let me use another color. What about, let's say orange. And this part over here, n plus 1 less than or equal to d. So that's really corresponding to invariant 0 underscore 2, which is the second one, right? We can only try to prove one invariant at a time. So just for compositionality, right? Okay, so hopefully that's that makes sense to you. You definitely should know about number one, the rule. Number two, the systematic generation of the proof obligation for different events and for different invariant conditions. And also precisely how to write them out as a sequence. Okay, let's now go back to the slides. And that's exactly what I have said, right? You can see this will be the complete way to really write it down. You can see I got exactly the hypothesis, and also I got the goal over here, either for invariant number 1 or for invariant number 2 over here, right? And also besides the sequence, I also put the name for the proof obligation. So this naming convention here is consistent with what you would see in rodent tool. They actually are consistent with each other, right? And the exercise view, which is extremely important. I only did 2 proof obligation over here for our initial model, but they are not complete just yet. I'm missing the proof obligation associated with the other events, which is MLN, because this one is only ML out, right? So for your exercise, you should really write down in the identical formats about the proof obligation that will be associated with MLN. Right? That'll be your exercise. You'll kind of see the solution for later exercises, but I would suggest you pause the video, or, well, I'm going to end the current video very soon. But before you move on to the next part, definitely do the exercise. Otherwise, you wouldn't know how to do them in the test later. All right? All right, so the conclusion for this part over here will be what's really so useful about systematically generating the proof obligation for different events and for different invariant conditions is because before you can ever claim that your model is correct, all the outstanding sequence associated with all the proof obligation must be proved or discharged. We haven't talked about exactly how to prove that. That will be the idea of applying inference rule, which we'll start talking about in the next part. But you should really know that once we have systematically generate all the sequence corresponding to the proof obligation rule, the goal will be to discharge or to prove all of them. Otherwise, you cannot claim that your model is correct. That's really important to notice. All right, so starting from the next part, we'll talk about how we can actually prove or to discharge the sequence.